Hi everyone. Tonight's discussion is about basic sampling strategies. We're going to be focusing on sampling methods for the next couple of weeks. And this is the beginning. We're just going to do some basic concepts in sampling. So our focal questions for this part of the course is, how do survey researchers design sampling plans? And what are some of the basic features of a good sampling plan? Okay, so I want to start with a pretty simple question, and it's a very relevant one for the times we live in today when so many surveys are done through email. Question is, why would you use sampling? Why not just simply invite the entire population to participate? Seems easy, right? Well, let's talk about that some. So inviting everyone to participate, in other words, simply sending to everyone in the population an invitation to participate, this can be perfectly appropriate. But there are some conditions that make it more reasonable or a better option. One is the population is small, the cost of data collection is low, and the sampling frame, meaning the best available list you have for invitations, is complete or very, very comprehensive. However, all of these conditions are not always present, right? And furthermore, sometimes cost, or what we call voluntary response bias, which we'll discuss in a minute, or coverage error, or some kind of combination of all these factors, they can actually make sampling a better option. So let's talk about that. Well, first of all, there's cost. If there's an additional cost to obtaining every additional respondent, whether that cost is in time, or that cost is in money, or that cost is both, then sampling can definitely be a much better option. What about voluntary response bias? Well, voluntary response bias is the idea that people self-select when they choose to participate, right? And self-selection, it can be fine if the effect of self-selection is kind of random and spread out over the whole population. But if self-selection means that you're really getting much higher response rates from some parts of the population and much lower response rates from other parts of the population, sampling can help you adjust for that, right? You can oversample from parts of the population that are less likely to participate, and then you can compensate for the potential bias. Similarly, coverage error, you maybe remember we've talked about this in previous weeks. Coverage error has to do with the sampling frame, or your best available list, the sampling frame, is not complete. This may mean there are real systematic differences between your population and the list you have, or the difference between the target population and the sampling frame is substantial and important and would give you biased results. Again, using sampling, you can overcome the problems with coverage error by creating a sampling plan that matches the actual characteristics that are in the target population. So, of course, sampling lowers cost, right? If there's an additional cost to every respondent. Sampling can also help address voluntary response bias by building some kind of proportional allocation process into the sampling plan. This is what I was talking about a minute ago, where what you would do is you would make sure your sampling plan is set up in such a way that you compensate for the problems you might have due to some parts of your population not responding in as high a rate as other parts of the population, then you intentionally oversample from those. And then furthermore, sampling can address coverage error issues when you be very intentional about analyzing the characteristics of your sampling frame and comparing those to the population characteristic prior to drawing your sample. Then you can use what you've learned in designing the sampling plan so that you can intentionally adjust how much you sample from that sampling frame for different subgroups, especially when those subgroups are not represented in the sampling frame in the proportions that they should be because of coverage error. So again, let's come back to the question, why use sampling? Why not just ask people we know to participate, or people we have easy access to? This is another alternative to sampling. Well, there's a lot of issues with that, right? This can be fine, just asking people you know, rounding up the usual suspects, kind of relying on friends and so forth. This can be fine if you somehow are a very special person that has access to a very representative sample, then it's fine. However, selection bias and the limitations of convenience sampling can cause big problems. Okay, selection bias is really, when the people you're selecting through the method you're choosing really don't represent the population. And convenience sampling is what we call it when you just access people that are convenient to access. So you really may not ever know, if you're doing a study this way, whether you really have access to people that represent the population, and so therefore this method can really result in a very biased sample. Sometimes we do social science research this way, though, but we're just very careful to identify the limitations of the study, like we admit up front. Well, we may not be representing this group or that group because we didn't have access to everyone in the population. Now you might say, well, why are all these things important when now with online surveys it doesn't cost any more to send to 5 people or to 500 people, and so we just should send out to everybody on the list. But again, it begs the question, is the list good? Do you have a complete list? So, to avoid problems with coverage error, or self-selection, or selection bias, or the problems with convenience samples, what you really want to do is get a very good sampling frame, the best possible sampling frame, and then analyze it before you send out your survey, before you do your sampling, to see how representative is it of the population, and then you can design your sampling frame accordingly. So to move on now, I want to just kind of go over a really basic process in statistics. Just review a couple of other things. How does the sampling process work? And some of this you probably know about. We've talked about it in this class or in other classes, but the first step in how a basic sampling process works is you define the target population. This may seem sort of obvious, but you define it in very specific ways so that you know who's a member and who's not a member. And then you may even need to include in your survey what we call screening questions, where you ask the person, basically a few things to let you know that they are in fact a part of the population. If it turns out they're really no longer part of the population, but you got their email address anyway, then you screen them out and you let the you thank them and you let them finish. So an example of this might be if you're charged with surveying all the teachers that work for a particular school system, you get a list of the email addresses. You might want to start the survey with screening questions and say things like, are you currently a full-time teacher working in a school that's a part of the blah, blah, blah school district? Because, remember, their list might have people who have retired, might be missing people who are new hires, and so on and so on. The next step is you examine, as I've been talking about, that sampling frame to see how good it actually is. You look for whether there are coverage error problems with that sampling frame. The next step then is you develop a sampling plan that matches the goals of your study. And this sampling plan should include some kind of process where you are randomly selecting from the population a representative sample. And here, of course, as we always say, the focus is on the estimation of parameters with as little error as possible, based on sample data that you believe is representative of the population. Okay, so with that basic background in mind of how the process of sampling works and so forth, I want to just tell you that then the sampling plan itself can take different forms, and there are different types of sampling strategies. And so we're going to walk through in this set of slides the first two, the most basic and the most commonly used. First one is what's called SRS, or simple random sampling, and the second one is stratified random sampling. So we're just going to go through that, what those things mean, and then in future sessions in this segment of the course, we're going to talk about some of the more advanced sampling strategies. And the other thing we're going to do in this talk is contrast stratified random sampling with blocking. And blocking is another kind of important research design feature that's used in social science research quite a bit, but it's not quite the same thing as stratified random sampling, but it's similar, and I want to just kind of contrast the two so you can get a picture of how they're the same and how they're different. Okay, so let's start with simple random sampling. What is simple random sampling? Well, SRS is a random sampling strategy that gives researchers a representative sample with a predictable amount of error. If you use simple random sampling, you can calculate, and we're going to do this in this course, what percent error do you expect if you get a certain sample size. And of course, the whole purpose of this is to ensure that you have representation from all the subgroups in the population. So you think of this as the hat method, so to speak, right? But it's the hat method with a couple qualifiers, which we'll get into. But the idea is everybody, in the population has their name on a little slip of paper. You put it in a big hat, you shake the hat really good, and you'll start pulling people out, right? Well, now keep that in mind, but then let's talk about what additional little qualifiers would have to be in place for the hat method to actually qualify as a simple random sampling strategy. So here's more of a formal definition for you. Simple random sampling is a random sampling strategy that gives every member of the population a known and equal probability of selection and gives every possible sample of a particular sample size a known and equal probability of selection. Okay, that's a mouthful, but just break that down and think about it. It's like everybody's got an equal chance of being in the sample, and everybody in the population can be a part of a certain number of possible samples, and all of those samples have an equal probability of selection too. Later in this portion of the course, we're going to contrast to another type of sampling method, which people naively think is equivalent to simple random sampling, but it's not exactly the same thing, where everybody in the population has an equal probability of selection, but every possible sample does not. So keep those two features in mind as we go through this segment of the course. Okay. So what's the process? How does this actually work? Well, we randomly select potential survey participants from the entire sampling frame. And this process tends to give us a sample that is representative of the population. And this tends to work really well when the sample size is really large and the sampling frame is really good. In fact, if the sample size you're drawing is very large and the sampling frame is very, very accurate, then you really don't need anything more than just simple random sampling. But the fact is we don't always meet those two characteristics. So researchers randomly select participants from the whole sampling frame using some kind of fair randomizing device. Okay, and we're going to define in a second what a fair randomizing device means. What does that mean? Well, simple random sampling with a fair randomizing device, what that does is gives every participant in the sampling frame a known and equal probability of being selected. Simple random sampling with a fair randomizing device also gives every possible sample of size n a known and equal chance of being selected. A fair randomizing device or process also handles duplicates and replacement. And what do we mean by that? Well, you have to have, as a part of your fair randomizing strategy, a decision rule for what's going to happen when you get duplicates. So you could get duplicates for a variety of reasons. You could get duplicates because you draw a name out of a hat, and then when you're done, you put it back in, you mix it up again, and you draw another name out. That's important. That replacement piece is important because you don't actually have an equal probability of selection for everyone if you pull a name out, put that in the sample, and don't put it back in. The next person, the probability is actually a little bit different. Think of it this way. Suppose we only have 10 people in our population. We're taking a random sample of 5. Pull the first name out. Well, everyone in that population of 10 had a 1 in 10 chance of being in the sample at that time. First person, their probability of selection was 1 in 10. But now if you don't put it back in, now you only have 9. Now the probability of selection for the next person is 1 in 9, and then it goes to 1 in 8, and and so forth. So it doesn't really work unless you replace the names back in the hat. And so the duplicates idea is that you have to have a decision rule that says when I encounter a duplicate, I don't take it for my sample, I just put it back in the hat. Okay? And every time I pull someone out, I record them, they're in the sample, but I put their name back in the hat. Now this is very complicated, and you can quickly see that the hat method, although it has like a certain sort of, kind of appeal, it's not really the best way to go. Okay. So let's do a little thought experiment. Let me describe to you 3 possible strategies that we could use to employ a fair randomizing strategy. All right, let's talk about the first one. Put all the names in a hat and pick names out of the hat until you've got the number you need. Second one, randomly generate numbers for everyone in the sampling frame and then sort by that random number, and then just take the first 20 or the first 50 or whatever the number is you need. The third method is take every 10th name on the list. Okay, now let's talk about which one is the best. Well, I'll give you a hint. I already told you that the first one doesn't work because the first one doesn't handle duplicates and replacement. The third one is pretty good, actually, especially if you take a random starting point from 1 to 10. If you do that, you take every 10th one until you get the number you need, that's awesome. Everybody in the population then actually has an equal probability of selection. It would depend on what the number is. Like you come up with the 10th, or whether it's the 11th or 13th or whatever, by dividing the number that you need by the size of or dividing the size of the population by the number you need, and then that's how big your interval has to be, and then you can start at a random starting point, and that actually gives everybody an equal probability of selection. The problem is what I mentioned a few minutes ago, what that does not do. That does not give every possible sample of a particular size an equal probability of selection. Because if you're taking every 10th one, you start on number 1, and then you get 11 and 21 and 31. A random sample that would include person 1, 5, and 7 is not even possible, right? So it doesn't give every possible sample of a particular size an equal probability of selection. In fact, some possible samples that could be fine and representative have no probability of selection under this method. So we're going to talk a little bit later about how you can use this method and what its strengths and weaknesses. But the bottom line is it doesn't qualify as simple random. The first one doesn't either, for all the reasons I explained about the hat method. Unless you pull a name out, look at it, record it, put the name back in, restir the hat, and do all that, and never take the same name twice. You check for duplicates. But that makes the hat method pretty screwy. So what you really actually do is the second method. And at some point in the class, I'm going to, just demonstrate this on the screen. Do it very easily in Excel. It's what I always do. What you do is you can program in Excel in 2 seconds generating a random number for every member on the list. And then when you sort by that random number, now you've got the population randomly ordered. And so then you just work, now they're in a random order, you just work down the list, you don't get any duplicates, you don't have any worries about replacement, and you meet all the requirements of simple random sampling. So that's something we'll demonstrate in class at some point, but it's an important concept. So the answer here is only the second one really works. Let me just restate all this now. The hat method can be fine if the population is small, the hat is really well mixed, and the slips of paper are replaced after each selection, and duplicates are handled. But generally, these are big ifs, and it makes the hat method really not a very practical or good strategy. Taking every 10th name, that's fine, because it does give every individual in the population an equal probability of selection, but does not give every possible sample size of size n an equal probability of selection, as we mentioned. So the list with random numbers works the best and is generally easy to do in a spreadsheet. Once the list is sorted by the random numbers, this process satisfies all our requirements for each individual, for the whole sample, and for the duplicate problem. So this method allows you to really take the whole sample all at one time. And so it really works the best and is actually fairly easy. All right, let's move on then to stratified random sampling. Stratified random sampling is a sampling strategy that gives researchers very specific advantages over simple random samples. So now let's talk about that. Well, it can help you handle like different group sizes, different sizes of different subgroups in the population, especially when those subgroups have different response rates and different variances on what it is that you're trying to measure. Well, how does it do that? Well, here's a formal definition. It's a simple stratified random sampling is a random sampling strategy that gives every member of a given strata a known and equal probability of selection and gives every possible sample of size n from a given strata a known and equal probability of selection. So this begs the question, what is a strata? Well, a strata is like a subgroup that you create. You divide the population into these strata, and especially when they're like meaningful groups that are related to what you're trying to measure, then that allows you to have a little insurance policy that you're going to have the number that you need from each one of the subgroups or strata. So how does it work? Well, you first divide the population into homogeneous subgroups called strata. And then we select the stratification variables or the basis for our subgroups because we believe that those subgroup membership things, whatever is defining those groups, whatever variable it is, we believe that those are related to what we're trying to measure with the survey. We believe it is related to the expected responses to the questions on the survey. So it works best when there are known similarities among potential respondents within the strata, but there are known differences on average across or between strata. So in a very simple example, if you know that there are well-known differences between males and females on some topic that you're surveying, and there's more sort of similarity within gender, but there are some differences between genders, then this can work really well, and you can design the stratified plan in such a way that you fairly and equally represent each gender, if that makes sense. Okay, so common stratification variables in educational research, they include things like school type. Like we often stratify based on, say, elementary, middle, or high school, or public school versus public charter schools, or public schools, charter schools, and private schools, that kind of thing. So school type. Also can work on location. Sometimes we stratify by region of the state, or by district, or say by the type of location. So something like urban, suburban, rural, etc. Other times we're most interested in respondent characteristics as stratification variables. So this could be, as I was mentioning, gender, but it could also be race or primary language or socioeconomic status or special education status or something like that. The way it works then is we randomly select potential survey participants within strata. And this process helps ensure that all the subgroups of interest are represented in the sample and in their proper proportions. Now, there are other ways you can allocate besides what's called proportional allocation, but proportional allocation is the most commonly used and the simplest. So think of it this way. If you divide your population up into a series of little smaller populations based on some variables that you think really matter to what you're measuring, and then you take a mini simple random sample from each one of those and then you combine them together, that's how stratification works. So we randomly select potential survey participants within strata using simple random sampling. And then the separate simple random samples from each of the strata are combined to make the full sample. So researchers randomly select participants from within the strata, but they do so using a fair randomizing device, just like we were talking about with simple random sampling. So very similarly then, the sampling strategy and device you use within each of the strata has to meet all the criteria that a simple random sample does. So there has to be a known and equal probability of any individual being selected, known and equal probability of any sample being selected, and you have to handle duplicates and replacement. So stratified random sampling, in a sense, builds potential non-response bias into the sampling plan, if that makes sense. So in other words, what you're doing is trying to anticipate that there might be, say, different response rates or different proportions of the population represented by different subgroups, and you build that into the plan. So this kind of method can be really helpful to increase statistical precision. By statistical precision, we mean like the margin of error. By including between strata differences in sampling variance in the standard error calculation, which then leads to the margin of error, which we'll walk through some of these calculations in the future as a part of this section of the course. What does this mean in plain language? Well, what it means is sometimes there's differences between subgroups and there's differences between subgroups, in other words, in their basic responses, but there's also differences in their response rates, and there's differences between subgroups in how spread out the answers are. Like some subgroups might be very lockstep with each other, little variance. Other subgroups might have a lot of different types of answers that can be given to a given question. All of that can be built into a stratified random sampling plan, and that makes it that can reduce your margin of error and give you more precise estimates than you would if you would just use simple random sampling. So let's talk about the differences between the two before we move on, just to kind of review. Simple random sampling can produce a very representative sample. It'd be great. However, stratified random sampling helps ensure that the total sample contains representatives from each strata within the population and in their proper proportions, if you're using what's called proportional allocation. So you see the difference there? In the first case, you're doing a simpler method, and you're basically trusting randomization alone to get you every subgroup you need. In the second case, you're building in a little bit of insurance policy for yourself by taking a series of little random samples across all the different groups and making sure that you're accounting for how many of each of those groups you need in order to get the total sample to be representative. Okay. Final topic, and this I know is a lot, but as we work through these different methods and you work on the project, I think you're going to get the basic concepts of each of these methods. Okay, so let's now talk about blocking. Well, stratified random sampling and blocking are very similar. However, they come into play in very different ways in the actual execution of a study. So, stratified random sampling is a method used for random sampling. Blocking is a method used for random assignment. And there's a difference there. Random sampling is what you do to draw a sample from the population that's representative of the whole. Random assignment is what you do when you're doing, say, a treatment versus control, and you want the two groups receiving the different forms of the treatment, you want those groups to be equivalent. So how does blocking work? Well, the way it works is we first divide the sample into homogeneous subsets called blocks. These homogeneous subsets are just like strata, right? They're just subgroups. And they're somehow formed based on variables that you think are important to what it is you're studying. So we select the blocking variable because we believe it's related to the expected outcome of the treatment within our randomized controlled trial or within our true experiment. So just like we pick the stratification variable because we think it's important to what we're surveying with our survey items, we pick the blocking variable because it's important to the outcome of the treatment that we're testing. And there's again very common things we use for blocking variables in educational research, and it's the same list as we had before, right? It can be school type, it can be based on location, it can be based on respondent or participant characteristics. And then what we do is we randomly assign participants to treatment conditions within the blocks, just like we were randomly selecting participants within the strata. But now we're randomly assigning them to treatment and control. So why is this important? What advantage does this gain for us? Well, it's pretty substantial. This process helps ensure that all subgroups of interest are represented in each of the treatment groups and in their proper proportions. So I hope you can see the parallel nature of blocking to simple random or to stratified random sampling, but it's about treatment and random assignment to treatment, not about random selection to be in the study at all. Okay, so again, what it's doing for you is creating like a little extra assurance that all the subgroups will be represented in both the treatment and in the control group. You can quickly see how it's a biased experiment if you don't have everybody represented in the treatment group and everybody represented in the control group, and all in their proper proportions based on which groups they belong to. In other words, think about it this way. You're trying to create a mini version of the population in both the treatment and control conditions. So then researchers randomly assign participants to treatment groups, again, using a fair randomizing device, just like we were talking about before. And the randomizing device has to function pretty much in this according to all the same characteristics that we were talking about before. Fair randomizing device gives every participant in the sample a known and equal probability of being assigned to each of the treatment groups. So you can kind of think about this as a very valuable and powerful research design strategy for building confounding variables into the experimental design. So you can kind of rule them out because now you know they're sort of equalized across the treatment groups. So blocking can also, in a very statistical sense, increase statistical power because you can use it to remove the error variance due to the blocking variables from the analysis, and that makes a more precise analysis. In other words, if you know that there's some of the variance that's due to this factor that you built into your design, then you can kind of pull that out and look more precisely at the effect of just the treatment effect. Okay. So remember, random assignment without blocking can produce equivalent treatment groups. Just like we said, simple random sampling can be fine. However, blocking helps create a sample within each treatment group that contains representatives of each block within the population and all in their proper proportions, giving you, again, a little bit extra insurance policy that you have representative sample of the population in each of the treatment conditions. And that's really important to creating a fair and valid experiment. So just like we said that you do a little mini random sample within each strata, well, it's the same thing here. Blocking is similar to creating a simple random sample within each block, within each treatment group. In other words, you're randomly selecting who gets to be in the treatment and who gets to be in the control group, but you're doing it within each block, and then you combine all of those. So the main advantage to blocking is enhancing the representativeness of each of the treatment conditions, just like stratified random sampling does that for the total sample in a sampling context. Okay. Remember too, this is getting sort of advanced research design stuff here, a little bit beyond the scope of this class, but researchers can use both. You can use stratified random sampling to ensure that the sampling process is fair, and then you can use blocking to make sure that the random assignment process is fair. In other words, think about, like, a drug trial. You want to know that everybody is fairly treated in the sense that all the subgroups in the population have equal chance to be either in the treatment or in the control, and that both the treatment and control are not biased samples, but they're representing the population. Okay, so we've looked at 3 research design strategies in this discussion: simple random sampling, stratified random sampling, and blocking. And let's talk just quickly to review what are the advantages and benefits of each of these 3 methods. Well, simple random sampling, big advantage: it's easy, it's simple to do, but you need to make sure you've got the fair randomizing device or process arranged and planned out so that you don't have problems with duplicates or you don't have problems with replacement. But it can work really great if you're pulling a large sample size and you've got a really, really good sampling frame. This works, gives you what you need. Stratified random sampling, however, can help build in extra insurance that you're going to have a really representative sample, because you're forcing yourself in a way by building into the design, taking multiple random samples from different parts of the population, or what we call strata. You're building that in so that now you're giving yourself a better chance of having all the important groups for whatever it is you're measuring to be represented in the final sample. And then blocking really is all the same stuff as stratification, but it's for random assignment to treatment conditions, not to random selection to membership in the full sample. So if you think about it in an experimental design construct, what you want is you take a representative random sample from the population, and then you have a fair random assignment strategy so that each of the treatment groups become a mini picture of the population themselves, so that you've got like equivalence. Okay, well, that's it for this week. We'll pick it up again next week with some more particular issues about sampling designs, and then we'll get into actually calculating the sample size needed and how you come up with the numbers involved in designing a particular sampling plan. Okay, take care.